Okay, biologists, it's Mr. B here again. The topic that we're going to go over now is a little bit mathematical, but I don't think it's anything too hard for grade 11 or grade 12 students. And this is calculating the size of critters in the field of view under a microscope. A couple things we have to consider when we try to figure out how big they are. We need to know what size of lens or what power of lens that we're looking through. The low power lens, you're zoomed out the most. And then as you move towards the more powerful objective lenses, your field of view shrinks. It gets much smaller because you're zooming in on your critter. What's amazing about this is every single field of view, that white circle that you look through, that bright circle, each of those field diameters is known. So it's kind of sort of like in every field of view, we've got a virtual ruler right there. And we can use it to measure how big critters are. See how far they stretch across that field of view. Turns out to be quite handy. The second kind of magnification you need to be really aware of is one called drawing magnification. When you've heard me say this before, if it's worth drawing, you make it a little bit bigger when you draw it in your field of view on your paper when you're doing biological drawings. If you've done that, you've also introduced sort of a drawing zoom or a drawing magnification that has to be sort of considered. So the point of this lecture is how big are these critters and what kind of drawing magnification did you introduce when you drew the critters? So those have to be reported in your biological drawings because, well, science is, if anything, quantitative. If you've introduced a change, we have to really know how much of a change that is. Okay, so let me turn on reflection and we'll get going. Boom. So I've taken the liberty of writing in a little bit of important information. You can't do these calculations without this. In this upper corner here, I've written low power, medium, high, and oil. Now what those stand for the sort of overall powers of lenses that you use in the microscope. The low power, and you guys are pretty well aware of this, I would think. The low power takes the ocular and multiplies it by the objective lens. There you go. The ocular is always a 10 times zoom. So where these numbers came from, I'm going to write in now. Ocular times objective gives you the overall magnification. So we'll just finish that off. And the oil immersion lens is the most powerful. It has a 100 times ocular and a 10, of course, multiplied by 10 for the objective lens, or sorry, for the ocular lens that is closest to your eye. So these zooms are fairly impressive, but you have to consider how wide the fields are. So in this case, we've got a little critter here below in medium power. So I'll draw a line through the middle, and what we know about medium power is that it is 1800 micrometers across. Okay, so let's back up a little bit. This is 1800 micrometers across. I just wanted to show you a stock example. Field diameter, right? Diameter, circles, sounds like math. We know each of their field diameters. We've measured them. And in grade 11, you did a lab which was very similar to this. You put a ruler underneath, or should have put a ruler on low and counted usually pretty close to about 4 millimeters. It actually turns out to be 4.2 millimeters. Multiply by 1,000, right? There's 1,000 micrometers per milliliter, or 1,000 micrometers per millimeter. There we go. Speak clearly. And we get lots of micrometers. Micrometers, you just take millimeters times 1,000. So here are our field diameters. 4,200 for low, 1,800 for medium, 420 for high, and you're zoomed in big time on the oil immersion lens, you're down to 180 micrometers. If you look closely, you might actually see a relation between low and high. Kind of see how they're sort of cousins, right? High is 10 times low. And medium and oil, if you look at them closely, it's like, whoa, oil is 10 times medium. Think about it. Oil is very seriously zoomed in, and it's a really, really tiny area that you're looking at. That area is so small of the circle that its diameter is only 180 micrometers. That's why oil is so blurry, and we have to do a little drop of oil to gather the light so it doesn't scatter and get super blurry on us. Point is, we know how wide these field diameters are. So how about we do a few calculations? Okay. So now that we have that information, we'll be able to use it for our questions. This one says, what portion of the field of view does this critter take up? So you have to make a little bit of a judgment call, but there we go. You'd probably be able to fit 3 of these little guys across here. Now, if you look at it, you say, okay, 3 of those guys across, if all the way across is 1800 micrometers, then each of those little guys is probably 6. If you don't see it, the way you do these is you take fraction, you take the fraction, 1/3, and you multiply it by the field of view. It's like dividing by 3 in this case. Fraction, or how much of the field of view just one little critter would take up, times your field diameter, FD. 1/3 times 1800 micrometers gives us 600 micrometers per critter. So I'll just write it in here without the units, and you get the idea. Yep, that would definitely add up. If it's 1800 across and 3 would go across, well, one's got to be 600 micrometers. A little standard math there for you. These questions get a little bit more interesting as we move on. Our little friend down here with the eyeballs, he probably takes up between 1/2 and 1/3. Kind of a judgment call. Okay, some people kind of include a little bit of the tail, but let's say, for the sake of example, that you, we'll change color this time, let's go purple, that you think he takes up about 1/2. So in this calculation, zoom in here, you take the fraction, he would take up 1/2, and you multiply it by the field diameter. Now you have to pay attention, it says that it's high. So let's do a little highlighting here. This is the high power lens. And you look back up here and you say, okay, high power, well, that's 420 micrometers across. So let's get back to our pen tool. 1/2 of 420 micrometers is about 210 micrometers per critter. Okay. Now, they can ask you, they could sort of throw you a little math curveball here, but these questions aren't bad. It would say, what portion of the low power field of view would this guy take up? Okay, now let's think about this. We know how big he is. So he's 210 micrometers. So let's throw that in. He's 210 micrometers as his real size. And we know that the low power field of view, we'll go up here, oops, undo. Low power has a 4200 micrometer diameter. Okay, so how much of that is he going to take up? Well, let's, if you haven't done this before, these units will cancel. You don't really need them. You can cancel the 0 above and below. And this simplifies to 21 over 420. Now, a little bit of math. If you think about it, 21 is half of 420. So crank this out and say, well, what do we got? You can grab your calculator. Some of you can figure this out in your head. But if you don't see it right away, it doesn't really matter. This isn't sort of a math class. 21 divided by 420 gives 0.05. If you think about that, he's on high power. When you're zoomed in on him, he looks large, but when you zoom out, he's really small. Okay, so the way you would say this is he would take up about 5% of that field of view. He'd be very, very small. Okay, very, very small. So that's a neat question where they say what portion, now that you know how big he is, what would it be like on low? Just put his number over low and see what it turns out to be as a number. That's all it really is. Okay, let's switch up colors. I think that's a good idea between questions. We'll go with brown this time. What's the size of the specimen? Now, when you look at this little guy down here, you figure how many of these guys could you set up all the way across the field of view? And I'm sort of drawing it loosely, and I know these got little fuzzies off to the side, this little germ. And I say, okay, what if it was about, say, 4 or 5 that go across the field of view? Really doesn't matter. I'll go with, in this case, it's reasonable to say, if you're looking at his little fuzzy edges, his actual size, the fraction, let's do a little zoom here. There we go. Each one takes up about a quarter, and he's on low. So 1/4 times 4,200 micrometers. Okay, so that's like 4,200 divided by 4. Oops. 4,200 per 4. I want to get this perfect. We've got 4,200 divided by 4 equals, there we go. Let's undo that. I knew that was messed up. The size of our critter is actually 1,050 micrometers. So each one of these little guys is that wide. We'll think of it that way. And a question like this, they're following it up with it, and they're saying, okay, if that's on low, so what fraction of the field of view would it take up on medium? Okay, well, I'm not panicked about medium. Medium is 1,800 micrometers. So think about it. If he's kind of, when we're looking at low power and we're zoomed way out, it would take 4 of these little guys to go across. But when we zoom in, it shouldn't be so many going across. Okay, so the medium power field, and if you forget it, you say, okay, medium is 1,800 micrometers. So let's go like that. 1,800 micrometers. And our little friend, he's pretty big. So if we put him in there, he's taking up, now crank out the number, he's taking up about, it's about 50, it's 0.58. Or you could say he's taking up about 58%, or just over half of the field of view. So if we looked at it, he would be like this big, okay, if I was just sort of roughly drawing it. All right, so what else have we got? Some interesting little questions that move on from here. These ones have all been fraction times field of view. And a couple of part B was saying based on the size that you figured out, what would it be like under a different field diameter. That's just straight math. Okay. Now we're going to get into a question where what they'll ask us is they'll ask us, well, what happens if you drew it bigger? At this point, let's switch up our pen color, we have something new to consider. You were figuring out the specimen actual size here, right? That was when you were figuring out that, for example. How big is he really? By doing that fraction times your field diameter. Field diameter of your field of view. Now, what you've done is you'll see this given there. It says, well, if they drew it 9 centimeters in length. Oh, wait a minute. Drew it on paper. Now what you've got is a drawing magnification. It's something new. That's not the magnification that the microscope was doing. That's the magnification that you're doing by drawing it bigger than it really is. And I always suggest you do that, because why would you draw something and provide almost no detail? Okay, so suddenly you panic and you're saying, oh, I don't want to do math. Mr. Sharcott once said that when you have a series of formulas, if you have a solution tree, it helps out. And that's exactly what I'm going to give you. It's a very simple solution tree. We don't need much space for it. You've probably seen one of these with density is equal to mass divided by volume. And this one, let's say done. Let's throw in the numbers in different color, blue for contrast. Your drawing size goes here. Your drawing size is equal to your drawing magnification, also known as Dr. Mag, times your specimen's actual size. Okay, we don't say actual size of the specimen. You probably can figure out why. The acronym would be a swear word for your derriere or your rear. Instead, we say specimen actual size. So what you've got is a formula which you can rearrange. So I'll just write a couple versions of it. ds equals Dr. Mag, or drawing mag, times SAS. Okay? These ones that are the side by side get multiplied by each other, so I'll just undo that. The rule is you put your thumb on the one you want to find and you look at the relationship of the other two. So if I look at Dr. Mag, oops, I hate it when it does that. Dr. Mag, I think I've got lost my tool. There we go. Dr. Mag, if you put your finger on that, you would have is equal to drawing size divided by SAS. I hate doing my fractions sideways, but we'll get away with it. And if you're trying to find your specimen actual size, if you think about that, if you put your thumb over that, you would see that you could take DS and divide it by Dr. Mag, or your drawing mag. There we go. So there's 3 arrangements of that formula. Come over here and we'll say, okay, so what would the magnification be if you drew it 9 centimeters in length? Okay, so if you drew it 9 centimeters in length, the first thing you identify, drawn 9 centimeters. Okay, this isn't exactly a word problem. You drew it. It's not, if you think about it, that's not the size of the critter. So you say, in Dr. Mag's pyramid, I guess if we put all the information in, there we go, that your drawing size was 9 centimeters. Now, it turns out you multiply centimeters times 10,000 to get micrometers. So this is 90. I'll put a comma in there to help you out. awful one, 90,000 micrometers. You say, okay, now I've got part of it. They're asking what would the magnification be? Okay, so they're asking for the drawing magnification right here. So if that's the one we want, then what is that there? Well, that's SAS. And the way you always find SAS is you take the fraction, kind of go back to A now for a second. What's the actual size of the specimen? Now, this is a really small dot, which is why you're supposed to pick the best lens for the job, because you're kind of zoomed out, and this is really hard to make a judgment call on. But I would say that 10 of these little guys, fraction, 10 of these guys would go across the field diameter. So if I took 1/10, and I said 1/10 times medium power, 1800 micrometers, then I probably am pretty safe. Let's push that in. So our critter's probably about 180 micrometers. So let's throw that in. SAS can be pretty easy to find. How many little guys would go across the field? I hit done, switch colors, and I want to zoom in so that we can see this pretty easily now. Let's go back to brown. So here is our sort of solution tree. So our drawing magnification, Dr. Mag, I like to call it that, is equal to 90,000 micrometers divided by 180 micrometers. The units will cancel because you've got micrometers on the top and bottom. Okay. If you want to make life even easier, you can cancel the 0 on the top and bottom. But let's just do this fast. 90,000 micrometers divided by 180 micrometers. What we got, or what we have, is 500 times. In other words, the top, your drawing is 5 right here. Your drawing is 500 times bigger than the actual critter was. 90,000 is 500 times greater than the real size of 180 micrometers. So now we know the rest of the story, which is what kind of magnification was introduced when you drew it larger. Okay, in a question like that, if it says anything about draw and it asks about magnification, it's asking you for the drawing magnification. So these are some pretty good examples. I'll leave this up on the website, and you can come back to it if you get stuck, if you need to see how these questions go. That's exactly why I do these. All right. So kind of in review, this takes longer than normally would. We started out by figuring out the specimen actual size. Okay? That's what this was all about. How big is our critter? And then, pretty quickly, we jumped into some comparisons. The critter's size compared to the overall field of view, and you know how much the field would he take up. That's lovely. I was much more interested in when we get to this little solution pyramid down here. So in question number 5, they'll say, what is the actual size of the specimen? So we're looking at something like a paramecium. Now don't be afraid with your fractions to say, ooh, how much of the field view does he take up? Okay, if it's not coming to you right away, it's not like he's taking up a quarter, it's not like he's taking up a half. You could say, sort of fair game to say, he's taking up, I need a new color. He's black, it's kind of boring. Let's use an annoying green. There we go. He's taking up about 2/3 of the field of view. Right? He stretches 2 of the 3 units across. It's a pretty good approximation. And because we're on low, got to pay attention to that. I've given you the information. It's 4,200 micrometers, depending on your microscope, but I'm using a stock example here. And what you get when you do that is you can say, well, he's probably 2,800 micrometers in size. It's pretty big. He's stretching across low power. Low power is pretty well the widest, right? It should be 4,200 micrometers across. He's taking up 2/3 of 4,200 micrometers. That's quite a bit. Pretty big. 2.8 millimeters to be exact, if you can divide by 1,000. So go to a question like this, zoom in, and it's saying, okay, if you drew him with a magnification of 20 times, how big should you draw him? Okay, that doesn't come up in class very often. Usually what you do is you draw it, and then you figure out what was your drawing magnification, sort of the lower left of the pyramid or the triangle. Let's, in this case, said, okay, if you had done a 20 times zoom for your drawing magnification, how big would you have drawn it on the page? You can just apply the triangle and you can figure this out pretty easy. Go like this, and I'll make it big enough now. So you fill in what you know. So your drawing size in this case is unknown, so you just write drawing size. You know that your specimen actual size, SAS, is equal to 2,800 micrometers. Okay. And you know that your critter, your Dr. Mag, or drawing mag, was 20 times. Okay, as soon as I see this, I know what to do. Drawing size on the top is equal to Dr. Mag, drawing magnification, times SAS. How do I know that? Put your finger over top of this one, like this, and these two are side by side. So you, on the bottom, you multiply them. So if my drawing mag was 20 times, if I drew it 20 times bigger than it actually is, what would I get? All right. Now, I'm not going to reach for a calculator. 2 times 28 is 56, and there are 1, 2, 3 zeros in there. Look at that. No calculator required. In micrometers, there's 10,000 micrometers in 1 centimeter. So I'll hit done, and I'll come back to my colors. Red should show up really well. Okay, so the decimals here. If you divide by 10,000, it's like 4 decimal jumps to the left. If you can't remember that, just remember that going from micrometers to centimeters is a division by 10,000. But I think you guys probably by this point in school know that dividing by 10,000 is 4 jumps to the left. Should be automatic by now, which is equal to 5.6 centimeters drawn in real life. Look, nobody draws things on paper in micrometers. They draw them in centimeters. So you're wrapping your head around the idea of how big this critter would be drawn on paper. You have to apply the pyramid. Okay? You have to apply this thing. Because if you don't, it becomes a lot more work than it needs to be. Right? And you've seen this pyramid before, as I said. Density is equal to mass divided by volume. So if you know how these pyramids work, once you put them in their right positions, density on the bottom equals mass over top of volume. That means division. And you could actually work backwards. Volume is equal to mass divided by density. but I don't want to hurt your brains too much. It's just formula rearrangement. There we go. Oh, look at what we have here. I'm not going to go on and do these. What these will always ask you for are the three parts of the pyramid. SAS, DS, drawing size, and drawing magnification. Those are the only three things that will come up again and again. Now, why am I torturing you with this? Well, guess what? When you draw something in Biology 12, I didn't ask you to do this in Biology 11, or when you look at you look through the ocular lens and down through the objective and you see something swimming around down there, you have to tell me it's SAS. And I want to know, once you've done your drawing size, most times you almost never figure out your drawing size, but what you will tell me is, oh, what's your drawing magnification? How much did you zoom it by compared to how big it really is? That's that little comparison, right? Your drawing versus actuality. Now that you have the pyramid, oops, undo. Now that you have the pyramid, you can make those calculations all day long. It'll be a little bit of a pain in the beginning as you do your calculations, okay? But you will know these very, very well. Now there are 14 questions here, and they constitute part of one of the very first labs you'll do in this course. And you have to get pretty good at knowing how to do these, okay? So keep an eye out for SAS. That's usually the first ticket. And then once you know SAS, look for them to give you the drawing size, right? And then you usually figure out the drawing magnification from there. Okay, so I've gone on and done my little math lesson. It's time to check out. Ladies and gentlemen, you can check this out a million times if you want, because it is now digital. Have a good one.